right, let's take a look at a couple of examples of determining the concavity of a function. So in example 1, we're asked to determine the domain and the concavity and any inflection points for this function. So let's begin with, we'll write the domain, f of x, the domain. Well, it's a odd root, and odd roots are defined for even positives, even negatives, for all real numbers. Domain is negative infinity to infinity. So I'll put that in interval notation. So there's our domain, check. All right, now concavity. So to do concavity, I need to figure out the sign of the second derivative around values where it's equal to 0 or undefined. So I need to take two derivatives. So let's do f prime of x. And that would be using the power rule, 5/3 x, and then subtract 1 from the power, and that would give us 2/3. All right, and now I have to take the second derivative, so f double prime, using the power rule one more time. So constant multiple, and then we're going to be multiplying that by the power. So that gives us 10/9. And then subtracting 1 from the power, we have x to the negative 1/3. Oops, negative 1. There we go. And then I can rewrite this. All right, so now I need to determine if there are any zeros of this function. And since the numerator has no variable, there are no zeros. But it is undefined. The denominator is 0 when x is 0. So f double prime is undefined when x is equal to 0. All right. So that's the point that I'm going to use, and use that to test to where the second derivative is positive or negative. So I draw a number line. And then I place the number that I found, the undefined value, which is 0 in this case, on the number line. And then I'm going to test the second derivative, evaluate the second derivative at points around 0. All right, so this was a 0 of the second derivative, and now we'll test around it. Let me pick, how about on the left side, if I pick -1, that x value, and I'll pick +1 on the right, and then let's evaluate. Okay, so I'm going to do f double prime at -1. All right, so if I put -1 in here, I get 10/9. This would be the cube root of -1, which is -1. And so that's -10/9. And that is less than 0. So on the left side of 0, we get the second derivative is negative. And then I evaluate the right side at 1. So that's 10/9, and times the cube root of 1, which is 1. So this is a positive number. So my second derivative is positive. And now I can see I have concave up on the left side since the second derivative is negative. I have concave up. F is concave up on the right since the second derivative is positive. And because the concavity changes, x equals 0 would be the location of an inflection point. So now I'm going to state that conclusion. So F is concave up. Then I state the interval where it's concave up. So that's from 0 to infinity. On the interval from 0 to infinity. And remember that you need to give a justification for that. So why is that so? Even though you did all this beautiful work, that won't count for your justification. You have to state a reason. So it's concave up because, and here's our reason right here, f is concave up when the second derivative is greater than 0 or positive. So we would say because f double prime is greater than 0. All right, let's state the other half. F is concave down on the interval from negative infinity to 0 because, and that reason is because the second derivative is less than 0 or negative. So whichever, however you want to say it. I find using the inequality a nice way to, a simple way to say that. All right, now we have to, so that takes care of concavity. And then we have one last part to take care of, and that's the inflection points. So F has an inflection point. And then at, now there's a couple ways that you could say it. Sometimes they just say at x equals 0 and leave it at that. They just want that x location. Sometimes you actually state the ordered pair, especially if it's very easy to evaluate. So if I put 0 into the original function, that's very easy to take the fifth, 0 to the 5/3 would be 0, right? So the ordered pair would be 0, 0, which is in the domain because the domain is all reals. So we could say it like this, or as an option, we could say at 0, 0. You don't have to say both. You just pick which one, or you answer the question as it asks. If it asks you for the ordered pair, you state the ordered pair. So F has an inflection point at the origin because, and we have to give a reason. Okay, so how do we know it's an inflection point? Just to recall from the previous lesson, in the previous video, we get an inflection point when the second derivative changes sign. That's what we're looking for. So I'm going to state that because, and here we go, we changed sign. The second derivative was negative, then it's positive. So I could say that because the second derivative changed from negative to positive, or I could just say because the second derivative changed sign. Because F double prime changed sign. There we go. And we've now answered all three parts. Let's look at example 2. Determine the domain, concavity, and inflection points for this polynomial function. Okay, so first, domain of y. Well, it's a polynomial, and so the domain is all real numbers. All right, check. I always like to kind of think of a laundry list. What are they asking me and checking it off? Make sure I've got all the parts answered. Concavity. Okay, to do concavity, I need 2 derivatives. So I'm going to go first derivative, y prime. Power rule for all these terms. So that would be 6x squared plus 18x plus 12. All right, that's the first derivative, but I'm doing concavity, and I'm not doing increasing, decreasing. So I need to go to the second derivative, y double prime. 12x plus 18. And now I've got the second derivative. All right, now I need to find where the second derivative is either equal to 0 or where it's undefined. Now, since that second derivative is a polynomial, it's linear, in fact, right? There are no undefined values. It's defined for all reals. But I could figure out where it's equal to 0. So I evaluate that. So I subtract the 18 over, divide by 12, and I get negative 18/12. And if I divide the numerator denominator by 6, I can simplify that to negative 3/2. All right, so I have found the root of the second derivative. That could be an inflection point if my concavity changes around it, but this is where my concavity is equal to 0. So now I'm going to draw a number line and test my second derivative around it. Okay. And so F double prime. Okay, so at negative 3/2, that would be where the derivative is equal to 0. All right, and so I want to pick 2 numbers around that. So how about negative 2 on the left side, and on the right side, negative 1. Okay, so evaluating the second derivative at those points. So y double prime evaluated at x equals negative 2. All right, so the second derivative at negative 2. So I'm plugging it into this here. So that would be 12 times negative 2, and then add 18. I don't really have to calculate that. That's negative 24, that's 18. That's going to be negative. So that's less than 0. So on my number line, I'm putting a negative there. All right, then I do the second derivative at x equals -1. Oops, I didn't mean for that to be curved. Oops, my eraser. Now I'm just making it worse, right? So the second derivative, evaluated, remember that's that evaluation bar. That's what I'm doing right there. So the evaluation bar, so it's y double prime at, and then I'm just doing this little subscript. It's supposed to be a subscript. It's hard to write small. At x equals -1. Okay, so the evaluation bar, which is different from the function notation, right? We'll have to get used to using both forms. All right, so now I'm substituting in -1 into the second derivative. So it's 12 times -1 plus 18. And I know that this is going to give me a positive value. So this is greater than 0. I'll mark that on my number line so I can kind of see. I like the number line to help me organize my thoughts. I don't have to use this. It's sufficient to write this out, do the algebra, but it's all about processing the information. So this helps me to visually think through what's going on. I do see a change in concavity. I have negative second derivative, so that means that I have concave down. The second derivative is positive. When it's positive, I have concave up. And when we change sign, that means we have an inflection point. So now I'm going to write all that down. So y is concave down on the interval. Remember, so this is an interval. So that's from -infinity to -3/2 on the interval, -infinity to -3/2. And then I say y, because f double prime is less than 0, or f double prime is negative. Hey, I'll be different because f double prime is negative. Okay, so you can say it in many different ways. Just has to be coherent. All right, so, and then my function y is concave up on the interval. Okay, so that's the right half. Now, it's not always like that. I know both these examples are showing negative to positive. You will see lots of variation. There will be times when there'll be negative, negative. So lots of things can happen, and you do need to test everything. Okay, is concave up on the interval from -3/2 to positive infinity. And then we give a reason, because f double prime is positive. All right, there is one more part to do, right? Because someone lift this up a little bit. We have to talk about concavity. So I've got, not concavity, inflection point. We just finished concavity. So let's say the last part. Y has an inflection point. All right, so the point, well, it's not very practical to substitute this into this function, right? They're not going to test you on whether you can get common denominator and add multiple, I'll do all these complicated for this number. So it's probably where you would just say the x equals -3/2. That would be sufficient for this type of problem at that point, because not f, because the second derivative, just changing up how I might say it, changes from negative. Oh, here's how they might say it, from negative to positive. That would be acceptable as well, just to write the signs there. Okay.